Hello everyone and welcome back to ECS 2200. So following our discussions on the basic principles of electrical circuits, today we're going to talk about Kirchhoff's laws, the current law and the voltage laws. We're going to start the lecture with defining these laws, and then we're going to learn how to write them, how to use these laws, and then in the end, we're going to solve a few examples so that we can practice them on different type of circuits. So up to now, we have learned about Ohm's law, and it was a very useful kind of tool because it actually relates the voltage and current of a circuit, of a resistor. However, it's not the most useful tool when we want to analyze a circuit, meaning that if I have a circuit like this, I need to know, other than the voltage and current relationship of each of these single resistors, like other than knowing what is the relationship between VL and IL and VC and IC and so on, I need to know what is the relationship between these voltages and between these currents, right? I need to know how IL and IC and I1 defined like this, and then IS are related, and how they are related to different voltages that you can see in blue in this schematic, right? So that is where Ohm's law is not enough, and we need another set of rules or set of laws. So that's where Kirchhoff's laws become very useful and they come into the play. Let me erase these parts, these notes. Okay, so what are Kirchhoff's laws? So we have Kirchhoff's current law, or KCL in short, which says that the algebraic sum of all the currents at any node in a circuit equals 0. And we have KVL, which says the algebraic sum of all the voltages around any closed path in a circuit equals 0. Okay, so let's first look at the KCL. So the KCL says the algebraic sum of all the currents at any node. So what is a node? Because, well, we're going to define it officially later, but then most of you or a lot of you might think that, or might have this impression that a node is where, well, we have some sort of an intersection in our circuit. Like if I have a, let's say, voltage source, some resistor, another resistor, here's a node, or here is a node. But the definition of a node is basically any part of a circuit that basically two or more components, terminals, are actually connecting each other. For example, in this circuit that I have here, this is also a node because a terminal of a resistor and a terminal of a voltage source are actually touching each other, right? It doesn't have to be 3 different wires, it can be only 2. But it's important that two terminals of two elements are actually two or more elements are actually connecting each other. So, for example, if I want to look at this circuit, looking at here, you can see that I have node A, node B, because node A is connecting R1 and Vs, node B is connecting R1 and RC, node C is connecting RC and RL, and then I can put a lot of dots here, but all of these are really node C. They're not new nodes, right? Why? Because I can simply connect this terminal of RL to this terminal of RC. Like, imagine that none of these exist, and imagine that I just cross off all this wire and I just use this line or this wire to connect them. I still have this node C here, right? So it doesn't matter if I have kind of basically a rectangular kind of shape for my wire. I could have like basically a spiral kind of a wire. As long as it's an ideal wire connecting two terminals of two different components or two different elements, the entire ideal wire, the entire piece of ideal wire that I have here is simply just one node. Okay, let me clean up here a little bit so that we can continue our discussion. So as I was saying, here's also node C, and the entire piece here is node D because it's a piece of wire, it's a piece of ideal wire that connects RL to Vs. Okay, so what does KCL say? it says that the algebraic sum of all the currents at any node in a circuit equals 0. Basically, it is telling us that, for example, if I want to write it for node A, I1 is coming to the node A and IS is going out of the node A. So I have to use different polarity, different signs for them. So I can say that let's write all the currents that are going out of a node in using a positive sign, and then use a negative sign for all the currents coming into a node. So in the case of a node A, I1 is coming into the node, so it's going to be a negative I1, and IS is going out of the node, so it's going to be plus IS is going to be equal to, we have a 0 here, right? So if I want to simplify this, of course, I'm going to get IS is equal to I1, which makes sense because, well, if you look at it, you can see that I1 is indeed is equal to IS because, well, there's no branching. So all the current, all the charges that are moving through through R1 are going to, well, continue their way, and then they're going to pass through VS. So I1 and IS, since we have defined them in the same direction of, well, clockwise, you can see that they are equal. If I want to write it for point B or node B, I can see that both of these currents are actually going out of the node. So I1 is plus I1 plus IC is equal to 0. Therefore, I can say that I1 is equal to negative IC, right? And again, it does make sense because, well, the same current, the same flow of charges are actually passing through RC and R1. So in one case, I've defined I1 going from right to left, and then in the other case, I've defined IC going from left to right. That doesn't mean that these are my definitions. I could have defined them in a different way, right? But since I've defined them in this way, I can see that I'm describing the same phenomenon. Basically, the charges moving from, let's say that we know the charges are moving from right to left, right? So I1 is actually describing the actual charge movement, and IC is describing the opposite of it. So we can see that why I1 is equal to negative IC. We can take another lesson from this as well, which is basically all of these things that we have here, all of these definitions, either for current or for voltage, the polarity that we use for voltage, the fact that we have decided here is positive and here is negative, or the fact that we have decided that the current IL is flowing from top to bottom in this branch, it's all something that we call it an agreement. This is the definition that we have actually come up with. IL is defined that way. It doesn't mean that charges are actually moving from top to bottom. It could be, but it's not necessarily true, right? So we have to solve we have to analyze the entire circuit until we can figure out what is the real direction of charge movement. Until then, we're just going to go with the definitions that we have, right? We're not going to basically think or assume that these definitions, like when I have this arrow here, it means that the charges are actually moving this way. I might end up having an IL that is negative, meaning that the charges were actually going the opposite direction. Or I might get a positive IL, which means that, well, the charges are actually going in the direction that is shown for IL. That is why you can see that for this circuit, which is a simple loop, it's a closed loop, so there's no branching, so all of these currents are supposed to be equal to each other everywhere in this loop. But you can see that sometimes we define the currents in opposite directions, right? Such as I1 and IC. Okay, so that's that. Now, if I want to write it for node C, I'm going to have basically IC is coming into it, so negative IC. And then IL is also coming into it, so negative IL is equal to 0. And then for node D, I have IS is coming into node D, so negative IS, and IL is going out, so plus IL is equal to 0. Okay, so it's as simple as that. And then for KVL, what we need to do is that basically we want to actually, so KVL is telling us the algebraic sum of all voltages around any closed path in a circuit equals 0, right? So if I start from any point, let's start from point A. So If I want to go around this closed path and come back to node A, the first thing I'm going to see is this voltage source. So voltage source is telling me that the potential in my circuit is going up when I move from node A here to node D here. The potential goes up by a voltage Vs. So I'm going to write plus Vs. Then I'm going to move all the way to here at RL. And I'm going to see that the potential is going down based on these polarities that are defined on VL. I'm going from a positive to a negative, so potential is going down by VL. So I'm going to write minus VL. Similarly, when I get to RC, I'm going to write plus VC and then minus V1. And then I'm back at node A, so this is all going to be equal to 0. So in previous courses, or some of you even in high school, you might have seen KVL, and you might have seen other ways of actually writing these KVLs. Sometimes people do it differently. They say that, well, when you enter something and it's a negative sign, just write negative. So they might write the exact opposite of way that I wrote it here. So they might actually write KVL as negative Vs. And then here, when they arrive at this resistor, they see positive, so they write positive VL. Then negative VC plus V1 is equal to 0. You can see that these two are actually similar. They're going to end up giving us the same results because the other side of the equation is 0. I can factor out a negative from any of the two. So for example, if I factor out a negative from the second equation, I'm going to get negative Vs minus Vl plus Vc minus V1 is equal to 0. Well, I can ignore the negative because the other side is 0, and then I have the same equation. Okay, so you can write it either way. Similarly for KCL. So remember we said that for KCL, if the current is coming into the node, I'm going to say it's negative. If it's going out of the node, I'm going to say it's positive. But I could have defined it exactly the other way around, right? I could have said plus I1 minus IS is equal to 0, and then, well, I would have got the same result, right? As long as you choose a notation, as long as you choose one way to write KCL or KVL and always stick with it, don't change your mind in the middle of the way, you should get the right results. Or not should, you must get the right results. There's no way that you get a different result, right? Unless you do some math mistakes on the way. So this is how you write KCL and KVL. We're going to practice it on a few other circuits and then also some examples as well. Okay, so let's look at a couple of other circuits and see how KCL and KVL are written for these circuits. So first, let's look at the circuit on the left. We're going to do KCL for this circuit. So this one I'm talking about. So as you can see, these KCLs are actually written here. So for node A, which is this guy, let me use red color. Yep. So for node A, I can see that I1 is actually going out of the node, I4 is also going out of the node, but I2 is coming into the node and I5 is also coming into the node. So you can see that I2 and I5 have a negative sign, I1 and I4 have a positive sign. I can look at node B. Here I have 5 different branches. I have I1 coming in, I2 going out, I have this IA coming in, I3 is going out, and IB is coming in. So I have 3 negatives, 2 positives. You can see that I have 2 positives, the first 2, and then I have 3 negatives. So you can practice this with other nodes as well. Make sure that you have actually completely understood this. I can do, so like this is a circuit with an example of KCL. On the right, we have another circuit that we can write different kind of KVL equations on it. As I mentioned before, we can have 2 different kind of methods. Similar for KCL and for KVL as well. We can write these expressions in 2 different ways. So let's actually do it for, let's say, for loop A here inside. Let's write it from, let's start from this node, this on the bottom left corner. So I'm going to start going up. I see V1, which I'm going from a negative to positive, so it's a plus V1. Then I have a negative V2, or minus V2, then minus V4, then plus VB, and in the end I have plus V3, and this is equal to 0, right? As I said before, I could have written minus V1 plus V2 plus V4 minus VB minus V3. I would have got exactly the same result. Okay, so this is one way. So method 1, it's not really a method, it's just that it's a convention. And then the method 2 is basically, I would write minus V1 because the first sign that I see when I arrive at resistor, this 1 ohm resistor, is a negative, so I write negative. And then the next one is plus V2, then plus V4, then minus VB, and minus V3 is equal to 0. Again, if I factor out a negative sign out of any of these two expressions, I'm going to get the other one. And since the other side is 0, that negative could be basically ignored. Okay, so the point that we can take from this example is that it doesn't matter which way you write it, you're going to get to the right solution anyway. Which one I'm going to use for the entire course that we have here is basically the first one. The reason that I do this is because it's more intuitive to me. I like to actually, when I get to a voltage source, I know that the job of a voltage source is to provide extra potential to my circuit. So I know that when I go from a negative terminal of a voltage source to the positive terminal of a voltage source, my potential goes up. So I would like to be able to write a positive VB, not a negative one. It's just more intuitive. It's just more connected to the reality. But mathematically, as you see, they're not different. So just use whatever you're more comfortable with and then stick with that convention. Do not change your convention from time to time, or like you're just going to confuse yourself. One other thing that we can see from this example is that not only we can write these KVLs in the closed loops such as A and B and C, if you see that we have a path D which is actually going around the entire circuit. So it doesn't really have to be a path that basically doesn't include or doesn't contain any other components or path within it, right? So you can see that this path D is basically going around the entire circuit. As long as it's a closed path, we're good. So I could have written path E here as well, by the way. Or I could have had a path F starting from this point, going around here, and then coming back, right? So basically ignoring the 3 ohm and the 4 ohm resistors in the middle, but and the 5 ohm, just starting from here. Maybe it's better to actually do it that way. Going this way and coming this way, back to the initial point. So that's path F. And you can define so many other paths. So basically, the important thing is that it has to be a closed path. Other than that, nothing. As long as it's a closed path, you can actually write a KVL on it.